Let's say you flip a coin. Normally it's either head or tails, right? But in quantum world, if a tiny particle like photon or electron were the coin, it could be in a strange state where it is both heads and tails at the same time. Until someone's look at it. This is called superposition. Let me explain more clearly about it. So the definitions of superposition is the ability of a quantum system to behave as though it is in several states simultaneously until it is measured. Tiny things like electrons or photons don't choose one state like being here or there right away. They kind of try out all the possibilities at once, but as soon as we measure or look at it, we force it to choose only one state. All wave functions have the property of superposition. In quantum physics, we describe particles using wave functions. These are like wavy patterns that tell us the chance of where a particle might be. These wave functions can combine and overlap, which is what superposition means. So, if a particle might be in two places, the wave function will show a mixture of both. Probability waves are used in quantum physics to depict particle states. There is a wave probability, a chance, that the electron or photon could be here or there or over there. That's what it means by probability wave, and it describes where the particle might be. Quantum particles are considered to be in a state of quantum superposition when they behave like probability waves. As long as the particle hasn't been measured, it's not in just one place or a state. It's in all the possible places or states at the same time. The probability waves shows this strange in-between reality. Any state that a quantum system may be in can be described by superposition, including location where it can be in two places at once, the electron spin where the particles can be spinning up and down at the same time, and the energy level where the particles can be having two energy levels at the same time.
Now, let's talk about the difference of superposition in classical physics and quantum physics. In classical physics, the principle of superposition refers to the additive combination of multiple physical effects. For example, when two sound waves overlap, they combine to produce a louder or softer sound depending on how they align. Similarly, if you throw two stones into a pond, the ripple from each stone overlap, creating a new wave pattern that is the sum of both sets of ripples. But in quantum mechanics, superposition is much stranger. It means that a quantum particle, like an electron, can exist in multiple states at the same time. For example, an electron can be in combination of both spin up and spin down states at the same time, rather than be limited to just one. We represent this mathematically as something like this. Psi equal to alpha times 0 cat plus beta times 1 cat. Here, 0 cat and 1 cat represent the basic states such as spin down and spin up for an electron. The coefficients alpha and beta are complex numbers called probability amplitudes that describe the contribution of each state in the superposition. When the system is measured, the probability of finding it in state 0 cat is the square magnitude of alpha, and the probability of finding it in 1 cat is the square magnitude of beta. These probabilities add up to 1, meaning the system will collapse into one definite state when observed. When you measure the particles, the superposition collapses into one of the possible outcomes. You will never see the mid-state directly, just one final result chosen randomly based on probabilities. This collapse doesn't happen in classical systems. Another key difference is interference. In classical physics, waves can interfere with each other, but in quantum physics, the interference happens between probability amplitudes and it can cause some outcomes to completely cancel out. So while both classical and quantum systems involve combining effects, only quantum superposition involves systems existing in multiple possible states until a measurement is made. This is one of the biggest ideas that separate quantum from classical physics.
Now, let's move on to the double slit experiment. This experiment shows that tiny things like photons or electrons can act like waves, and those waves can be in superposition. From this simulation, we can see that the light is shone into the slits. If only one slit is open, the light just goes straight through the open slit, and on the screen, it appears a single vertical line of the light directly behind the open slit. If both slits are open, we are expecting two vertical lines on the screen, one from each slit, just like the one from the video. However, as if every electron has passed through the two slits as a wave, the experiment captures an interference pattern. How can this be? This pattern only makes sense if the light takes both paths at once, which is the superposition. And it is even more surprising if one electron is sent at a time, and we still eventually get the same interference pattern over time. So, from the experiment, it shows that the electrons interfere with one another in some way, causing them to arrive at different locations than they would if they were alone, even if one electron is shot at a time. And if we measure which slit the particle goes through, like placing a detector at the slit to watch it, the magic changes. The pattern on the detector screen subsequently changes into the particle pattern of two strips. There's no longer an interference pattern. So, the double slit experiment shows that the quantum particles like photons and electrons don't just go through one path. They go through all possible paths at once until measured. So that's what it meant by superposition.
One of the most important real-world applications of quantum superposition is in quantum computing. Unlike classical bits that can only be 0 or 1, qubits can be in a superposition of both 0 and 1 at the same time. For example, while a classical bit is like a light switch that either on or off, a qubit is more like a spinning coin. While it's spinning, it's not just head or tails, but kind of both at the same time. Only when you stop the coin and look does it land on either heads or tails. This ability to hold multiple states simultaneously is what makes quantum computing so powerful. With n classical bits, you can represent only one value at a time, but with n qubits, you can represent 2 to the power of n combination at once, thanks to superposition. That means with just 10 qubits, you could store over 1000 possible states simultaneously. This enables quantum computers to process many possible solutions in parallel instead of checking them one by one like classical computers do. But superposition alone is not enough. Quantum computers also rely on interference, which helps amplify the correct answers and cancel out the wrong ones.
The principle of superpositions allows the technologies to evolve. It has been applied in quantum sensor where it enhances the sensitivity of measurements in atomic clock and gyroscopes. Superpositions also helps in the field of quantum metrology with the innovations of magnetometer, gravitometer, and interferometer, where the metrologists use to measure gravity and magnetic field. Superposition allows the expansion in quantum imaging where superposition-based states allow imaging beyond the classical diffraction limit, improving the resolution. And lastly, in the field of quantum biology, although most of them are still debatable, however, the application of spin superposition used by the bird migration to detect the magnetic field using protein known as cryptochrome, and in photosynthesis, superposition of energy states and paths improve energy transfer efficiency.
To conclude, quantum superposition is the ability of quantum system to exist in multiple states at the same time until it is measured. This means a particle like an electron can be in more than one state at once. A famous example is the double slit experiment, where the particles act as if they go through both slits at the same time, creating an interference pattern. Although it seems strange, quantum superposition is the basis for real-world technologies such as quantum computers, highly sensitive sensors, and even some biological processes. In short, quantum superposition is not just a theoretical concept, it is a fundamental principle shaping the future of technology.